Welcome everybody and the Unit 5 series. Let's start talking about section 5.6, which is all about reaction energy profile. We used to find some certain type of reactions in terms of exothermic reactions or endothermic reactions. But the question is, how can I represent these type of reactions in terms of graphs? The first thing that we have to keep in mind that we have a y-axis and x-axis. The y-axis is labeled with potential energy, whereas the x-axis is represented by reaction progress, and sometimes it's called reaction pathway, and sometimes it's called reaction coordinates, which is going to be used a lot. Okay, so first of all, what you have to know about the exothermic reactions, if we have, say, let's say A plus B equals C. So as we can see, A and B are reactants, whereas C is the product. And from the graph that we can see in here, the energy of reactants, I mean, like the energy of A and B, is greater than the energy of C. So at that point, we have to say that the reactant energy is greater than the product energy. And that's why if we want to take the value of delta H, which represents the products minus reactants, the sign will be a negative. And that's why this is a good indication that the negative sign refers to an exothermic reaction. And the exothermic reactions, which is another thing that you have to keep in mind, leads to increase the temperature, which means the energy is released. You have a reaction and a calorimeter. If it's exothermic, then the temperature will increase. And that's why we can deduce that there will be a transferring of energy from system to surroundings. So this is an indication of an exothermic reaction. One more thing to be discussed with you. At the top of this graph in here, we can notice that it has a name. And this name actually is represented by the activated complex. And the activated complex, from its name, it's complex compound. It describes a certain type of compounds that is between products and reactants. It's not a product, it's not a reactant, but something in between, and it's highly unstable because it has high potential energy. We call the, let's say, the magnitude that extends from the energy of reactants to the top, which is the activated complex, the activation energy. And the activation energy has a definition, which is the minimum amount of energy needed to start the reaction. So if the activation energy is really high, then the rate of reaction will be very slow because you need to supply the system with a great amount of energy in order to react. So for example, if we compare this, just want to erase all of this stuff in here. The second graph actually represents an exothermic reaction, but there's a difference. Okay, let's start with the common things. This is 1 and this is 2. In 1 and 2, both reactants energies are greater than the energy of products. So this is something in common. But if we look at the activation energy for both, the activation energy for 1 and the activation energy for 2. My question, which of these you expect to be slower? Okay, your answer is correct. 2 is slower because it has higher activation energy. But keep in mind something. If I ask you what's the magnitude of the activated complex energy, in here you have to say um, it's from here down below to the top. So imagine that it's really great amount of energy. This is highly unstable. So one more thing to be discussed as well, the higher the potential energy, the less stability or less stable becomes. So if your compound, or let's say, for example, if you look at this in here, which of these is more stable, the reactants or products? Since the products have lower potential energy, then they'll be more stable than the reactants. And the least stable species in this here is the activated complex because it has the highest potential energy. And now we're done with potential energies and their stories, and exothermic reactions for sure. And now let's go to the opposite of exothermic reactions, which is the endothermic reaction. So let's take more example about it. Let's look at the guy in here. This is an example of endothermic reaction. As we can see, the energy of a product is greater than the energy of reactants. And that's why if we take the delta H, which represents the energy of a product minus reactants, the the sign of delta H is going to be positive, and it's reflected on the value in here. So the delta H, which is, I just want to draw in red color, this one in here, this is the delta H. And sometimes, or most of the cases, we represent the delta H in endothermic in terms of arrow with upward direction. For exothermic reaction, it's represented by an arrow with downward, just like keep in mind, sometimes it's mentioned. And the same thing here, we have potential energy and the y-axis, reaction progress in the x-axis. And this is the activation energy, which is from reactants to the activity complex, which is EA in here. And one more thing, if we have a reaction in the science lab, I just like insert a thermometer, okay, and this reaction was endothermic reaction. The reading of the temperature will decrease because the energy transfers from surroundings to system. And the reason behind transferring the energy from surrounding to system, because I need to supply my system with amount of energy in order to make products with higher amount of energy. So in endothermic reactions, the temperature decrease, the transferring from surrounding to system, and the delta H is always positive, etc. In your IP exam, you may be asked to complete the graph. For example, they can give you this graph in here and just complete for endothermic or exo. So if it's endo, you have to increase the energy in here, show them the activation energy. If it's exothermic, you have to show them like it's lower like that. You have to label the x-axis and the y-axis potential energy. Like do not write abbreviations, write the full name. In addition to the reaction coordinates, which of these reaction is faster, and actually it's based on the activation energy. If it's really high, then the reaction will be very slow, etc., etc.